Swayam Prabha. Digital India. Educated India.
So, in today's lecture, we take up this absorption unit operation and we address mass transfer rate and hydrodynamics. Okay, and if you recall, we said earlier that we can have continuous process or we have stage wise process. Typically, absorption is done in a continuous packed bed. So, we have a packing and two streams, gas phase and the water phase or the liquid phase, they are brought in contact through some packings. And similarly, we can have a co-current process or we can have a counter current process. And if you recall, we said that in counter current continuous contact process, the driving force is more large. So, in which case we have a shorter column. Okay. So, now we take this absorption column, continuous counter current packed bed column. Okay. So, what we have here is absorption. We look at continuous contactor. So, essentially we have packed bed and we have counter current flow. All right. So, schematically we have an absorption column like this and packing we denote with this cross. We have a stream of gas effluent with mass flow rate G1 kg per second or mole per second. We have GS, which is solvent or solute free basis flow rate, so which is G1 into 1 minus Y. We have mole fraction, which we can write in terms of solid free basis mole fraction, and which means we can also write this as G1 over 1 plus Y. So, you must check yourself how we are writing GS in terms of mole fractions Y and how we are writing in terms of mole fraction but solid free basis. Okay. All it means we can also write Y1 as Y1 over 1 minus Y1. So, this gas phase is brought counter currently in contact with the washing liquid solvent. It has a flow rate L2. So, we denote here 2, we denote here this 1. So, we can have LS, we can have X2 and we can have capital X2. The gas effluent which leaves from here treated or vent or exit. Okay. This has flow rate G2 or GS. GS same as this GS because it is a solvent flow rate Y2 and capital Y2. 1, we have this spent liquor or spent liquid. This has a specs L1, LS, X1, capital X1. At any cross section, we can write L, LS, X, capital X. And here in the second phase, we can write G, GS, small y, and capital Y. Make a notice here that GS, GS, GS is a constant here, remains the same. LS, LS, and LS, they remain the same because these are all solid free bases. Now, if you look at the equipment, there are two types of equipment. One is a stage wise and one is a packed bed. Packed bed is the most common for absorptions. Stage wise or tray wise, mostly common for absorptions. But there are some industrial distillation column where we have stage wise trays also. In which case we have trays, they are perforated, liquid trickles from one stage to another stage, and we have the gas which flows through this through this trays. Okay, so schematically this equipment, if you discuss here, then we can have the trays like this. Although it's not very common for absorptions, distillation it's widely used, and these are perforated. Okay, this gas to be treated flows through this, and the liquid which comes from here, it flows like this through this. So there is a pool of liquid on every trace. Okay, and it makes an exit here, and the liquid makes an exit here. So this is like trace wise operation or stage wise operations. On the other hand, which is the most common here, is a packed bed. So when you have the packed bed column and you look at the packing, there are several types of packings. Now it's recommended that you go through the textbook or go through some handbook and become familiar with the several types of packings which are used. Packings are also, they have the specifications. So any packings material you choose or which is given, they have certain specifications. For example, first thing is these are regular packing. There are regular packing, or we can have irregular. Okay, regular packing also sometimes we have very engineered or structured packing. Okay, so of course the cost is also involved here. These packings are very expensive, cost is generally very high. But when we say regular packings, so one common packing would be what we call rashing rings. So if you look at some of the regular packings, so we have rashing rings, which is nothing but a cylinder shell. All right, so it has length, it has inside ID and the thickness. All right, we can also have lacing rings. So there are several types of packing. Lacing rings, so they are also cylindrical, except that there is a partitioning inside. Okay, we also have burled saddle. Okay, so certain geometrical configuration like this. One can also have a spherical, spheres, the beads. So these are all regular packings, and if you look at just one packing, for example the simplest, this spherical beads like this, there will be a film of liquid. All right, so liquid, if it flows like this, it will trickle like this, it will make a film around this, and the gas will flow, go past this, and the gas will diffuse inside the liquid. So similarly, if you have packing like this, made of racing rings, then there will be inside, there will be thin layers of liquid, and the gas will flow through this these packings or this rashing rings. Okay, and structured packings or engine packings, they are also very very specific, but they are very cost effective. The idea here is that all of these packings, they have certain meter square per cubic meter, so specific surface area, and that's the parameter which plays a major role if you should be able to realize in mass transfer. So when we say there is a flux of certain species which will diffuse from one phase to another, so there is a moles per second per meter square. So there is the interfacial area between the two phases, and idea is that choose that type of packing which gives the largest area, largest interfacial area or contact area in a small given volumes. So 1 cubic meters, generally everybody prefers a very larger meter squares, so that the total amount of solid transferred from one phase to another phase is very large. All right, so all of these specifications, going back to this, they are characterized mostly by meter square per cubic meter. What is the specific surface area of these packings, which we said, like a sphere, burled saddles, or lacing rings, or the racing rings. Okay, so if you look at any handbook, or if you look at some table, you will see, say, type of packing. Okay, so it's encouraged that you go through some of the handbooks, say Perry's handbook, or go through Treball in a mass transfer, or Maccabee Smith, some of the books which we are following in this course, or reference course, and they have given, they have a very nice table, and they have tried to include most of the regular packings which we use. So if you look at type of packing, there will be serial number 1, 2, for example, type of packing, then there will be material here. So maybe it says ceramic. So most of the packings, maybe they are made of ceramics. It's also possible that they're made of alumina, okay, stainless steel, etc. So the material of construction of the packing. Then there will be a column for AP. So this is the AP which we are talking, meter square per cubic meter. Now this meter square per cubic meter is of course our engineering parameters, but very often manufacturers also supplies another very common name, packing factor, FP or CF. So we'll talk about these parameters. They are used in some design calculation, etc. And then you will see a schematic of these packings, whether they are spherical, or or it's racing rings, or it's a lacing rings with partitions, or you have this burl, saddle, etc. So it's recommended that you go through these tables given in most of the textbooks. All right. So typically, whenever you choose the packings, of course, one favors very large meter square per cubic meter, but these are also important things to note here, that these are also design considerations. For example, when you choose a packing, then what are things generally one looks for? One would be of course AP, meter square per cubic meter. So it should give us reasonably very large contact area. But the more important also is here is material of constructions, because depending upon the type of fluid, we must ensure that this is corrosion resistance. For example, if you use sulfur dioxide, then you must use, or you will like to use ceramic, which is corrosion resistance. Okay, you can also have packing made of plastics. So if you're using sulfur dioxide, there is a strong likelihood that this um, plastic packing will not work. So packing specs would be AP, materials of construction, of course the cost play a major role. If you have structure packing or engineering packing, or a structure packing, and these are very very expensive. All right, so the cost also plays a major role. So these are the things, these are the three aspects one generally looks for while choosing a certain type of packing here. Packing could also be, as we said, regular, or we said irregular. Essentially it means when we packed, they are randomly they are packed. So if you have one packing sitting like this, another packing sitting like this, another packing sitting like this, so it's at randomly packing we have in case of absorption columns. And if you look at this absorption column, typical schematics, you will have a shower. So when the liquid flows from the top, it has to go through a regular shower, so that water or the liquid, it distributes itself over the packing. And when similarly when the gas is sent from the bottom, there will be some distributor. So typically if you will draw here, you have a column, then you have a distributor. So there will be a shower like this. All right. So the liquid, it will trickle from here, it will go through this pack bed, and here you have gas going through this. So there will be some distributor here. So you have a distributor, you have a shower, okay, and here you have this packing material, which is randomly packed. All it means, if you look at very carefully, suppose you have a very simplest spherical beads, another beads sitting next to it, another beads sitting on top of it, another bead sitting here. The hydrodynamics is quite complex. You must appreciate that in this case hydrodynamics is complex. All right, you do not have a situation like this where you just have one sphere and it forms a regular film, water forms a film here, and the gas goes past this the film on the packing. Generally all this is very complex dynamics. If you have one packing like this, another packing like this, another packing like this of racing rings, then you can imagine that the flow here is quite complex around this, either the water flow rate or the gas flow rate. So it's very difficult to analyze. All right. These days, if you heard of CFD, computational fluid dynamics, computational fluid dynamics. So one makes use of this CFD to resolve this complexity of hydrodynamics in two-phase systems like this we have in case of F-jobs and columns. So generally what happens when it comes to engineering design, then hydrodynamics is not solved to that extent, the way we do it in case of CFD. Now what we do here in case of F-jobs and column design or similar unit operations, one has a macroscopic analysis. All it means, water flows from the top and gas flows from the bottom. So if you have two counter current flows, from engineering point of view or from the operation point of view, it should be loading and flooding, which should be the main concern. You can imagine that if the water flows is very large, gas flow is very small, the entire column will be flooded with water. It will prevent gas to go from the bottom. Similarly, if the gas flow rate is very large and water flow rate is very small, gas may prevent water to flow from the top, and the entire packing will be flooded or loaded with the gas. So these are like more of a macroscopic analysis. Instead of getting into complex fluid dynamics, velocity profile inside the packed bed column, by making use of the CFD, one looks at macroscopically. What is the superficial velocity? If you recall, we talked about mass transfer coefficients as an engineering parameters. Here you can think of why do we need this mass transfer coefficients. If the hydrodynamics is very complex, we do not resolve the fluid profile around the packings. There could be a boundary layer, there could be film layer, right? All we are concerned with, what is the rate of mass transfer. In that case, if you recall, we said that J mass transfer is Km mass transfer coefficient. We can write that Cb in one phase and maybe Cs on the other phase. In this case, maybe it's a liquid phase. Now this is a mass transfer coefficient, which we said that it's related to Sherwood number, and this is related to Reynolds number and Smith number. So all we do in as far as engineering is concerned, design is concerned, we look at the Reynolds number which is superficial velocity V0, packing, so certain characteristics length Vd, rho over mu of the fluid, and rho density of this fluid. So we look at Reynolds number, we calculate Sherwood number, and then we have this mass transfer coefficient calculated to obtain our flux here. In other words, entire complexity of hydrodynamics, is embedded in this mass transfer coefficients. We do not solve velocity profile local, V as a function of R or V as a function of Z, which we can do by using this computational fluid dynamics. Okay, so we try to understand, we must appreciate here that hydrodynamics in a typical F-jobs and column, or for that matter in most of the unit operation, is very complex. It's not like we have a simple open tube and Reynolds number is say 2100 or less than 2100 and 100, we have a very nice velocity parabolic profile. If you have packed bed columns which is packed with different type of packings, simplest would be spherical beads. Even in the case of spherical beads, if the Reynolds number is very small and these packings have been they packed randomly, the velocity profile around any sphere, any beads will be very complex. It's not possible to resolve unless until we make use of CFT and we try to solve local velocity profiles. So most of the times we have very macroscopic analysis. All we need a Reynolds number. If a Reynolds number is known, we can calculate Sherwood number, we can calculate mass transfer coefficient. The second or the only most important hydrodynamics which we consider is loading and flooding. We ensure that the column is running under very safe and smooth conditions. So that's the only hydrodynamics which we have for this course mass transfer 2. Alright, so we look at this hydrodynamics of loading and flooding before we start mass transfer aspect. Okay, so in this lecture we look at very small aspects of this hydrodynamics, but it's very important. We said we have loading and flooding. All right, and we must realize that this will happen if we have situation like this, counter current flow. So if liquid velocity is very large, all right, it's possible that we will have flooding. If gas velocity is very large or flow rate is very large, what do we call? We have this loading. And a safe operation demands that there is neither loading nor flooding of the column. Okay, so that's one thing. And the second is of course pressure drop. One would be interested in finding pressure drop per unit length or per unit height of this column. Now pressure drop in a packed bed column is very similar, or at least you can make an analogy. Pressure drop, if you recall, we did, or you must have done in some at the second year levels, or in fact at the first year level, flow through the packed bed where you have Ergun equations. All right, so Ergun equation can be applied to find the pressure drop. Okay, but there if you recall, it's a stationary phase. We have a very nice packing arrangements. We have some certain packing porosity, sphericity, we have certain Reynolds number, and then we have analytical expression obtained based on the viscous term and the inertial term. We write the pressure drop as a function of V and V square. So this is the analytical equation of course we obtain, or one has obtained, one can obtain starting from the first principle. But generally in case of this packed bed column, when we have counter current flow, very often we have to rely on certain correlations, or we rely on certain graphs which have been prepared by the manufacturers or by certain experiment under certain experimental conditions. Okay, so of course Ergun equation can be applied to get an estimate for the pressure drop. One can work on this relative velocity, assuming that one phase is stationary, etc., to obtain this pressure drop. But generally it's not it's seldom done. One has several such graphs for pressure drop for different types of packing, given in most of the textbooks. Okay, so one very common plot, very classical plot for this counter current flow in a packed bed column, which we are applying here, the absorption is given by Eckert. Very classical plot here. So we look at this plot and try to be familiar with this. So this is a very old plot of 1938, and there has been several modification or update, maybe by Pickford later, to determine or do some analysis for this loading, flooding, and the pressure drop. So it's a very classical plot. It's recommended that you become familiar with this and solve at least few problems, or address certain examples here. So this plot will look like this. On the x axis you have L prime over G prime. Okay, we'll talk about this. And you have rho G over rho L minus rho G to the power half. So this L prime and G prime, of course L denotes for the liquid phase and G denotes for the gas phase. The unit of this is kg per second per meter square. So it's very specific, unit specific. One has to go by this units here, kg per second per meter square. And here on the y axis we have G prime again, square Cf mu L over rho G, rho L minus rho G, and you have this Gc here, which is of course 1 if you use SI units. Okay, this G is kg per second, kg per second per meter square. So we understand that this is G prime. So far we have used the nomenclature Lg or Ls and Gs, which is kg per second. Okay, so this also a mass flux kg per second per meter square, and we'll make use of this to determine the diameter or the size of the column. All right, so let's come back to this. One has to calculate the y, and one has to calculate this x here. Cf, if you recall, we talked about this packing factor. So the manufacturer or the handout of that packing which you have chosen should have given this Cf here. Okay, we have several lines here, like this, like this, like this. You will see the last line, this will be marked as flooding line. Okay, and here you have some numbers like 0.1 etc., and each curve will have a certain numbers, which is say 12, 1200, 250. This is Newton per meter square per meter. So if you recall, this is nothing but your pressure drop per unit length. So this is what we have, right? So this is a plot, the graph, very classical plot given by, prepared by Eckert. Some improvement here or some changes, as given by Pickford. It's very important that you become familiar with this and how to use this. Okay, so more important here is to calculate x. So if you calculate any L prime by G prime, it's very easy to see that if we increase this number here, keeping G prime constant, it's possible that we hit this flooding line. All right, so it's whenever you do this analysis, suppose we fix G prime, which means we have fixed the gas flow rate, and we increase this, we have flooding line here. So for a given this y abscissa, we have fixed here x axis from which we can calculate L prime. So this will give us a limit for the flooding line, and here the pressure drop of course exceeds very high. Generally operating curve or operating condition is 70% of the flooding conditions, of the flooding limit. So we are talking about this limit here. So now if we work on say 70% of this, say if this is a 70% of the line, then one can calculate L prime and G prime. One can calculate this y axis here to work on this. So that's one thing. More important here to note that we are working on the quantity like G prime and L prime, which we said is kg per second per meter square, which means if we know this quantity, either L prime or G prime, and if we know, or we should know, G and L actual kg per second, then from this we can get cross sectional area of the column. So it's hydrodynamics which gives us cross sectional area of this column. If G and L are fixed, because generally these are given to us or given to the designer, that we have certain kg per second of gas and certain kg per second of liquid, which is like a solvent to treat this effluent. Then it's a hydrodynamics which will dictate us what should be the size of the column. And when we say the size, the diameter, not the height. Height comes from mass transfer, diameter comes from hydrodynamics. Okay, if we have very large diameter or relatively larger diameters, and if the flow rate is fixed, that means the superficial velocity will be smaller, pressure drop will be smaller. So this is how we get into this pressure drop, that if we increase for a given g prime kg per second per meter square, if we increase L prime, we hit the flooding line here. Okay, so if everything is fixed here, one can obtain from the flooding line what is your maximum L prime, which is required as far as hydrodynamic is concerned. Okay, so again, going back to this design aspect of an absorption column, you must not forget that we have hydrodynamics and we have mass transfer, and very often it's an iterative process. Mass transfer may demand, given certain type of problem, that I require 1000 kg per second. Okay, but it's possible that when we get back to this curve, 1000 kg per second of the liquid flow rate might give you an operating curve which is very close to this flooding line, or it's on the flooding line. That means one has to come back, reduce the size of the, or change the size of this column, redo the calculations for mass transfer. So the two, they go parallelly, they're not in like series. One has to do this kind of iteration. We will take an example where we have the mass transfer requirement, and then we have a different hydrodynamics requirement. Okay, so hydrodynamics comes from loading and flooding, and one of these curves will also give us how much is the pressure drop, del pressure drop per unit length. So look at this unit, Newton per meter square per meter, which means the length should also come from somewhere else. So that's a mass transfer. Alright, so mass transfer will tell us how tall is the column. Hydrodynamics in general tells us what is the size of this column, cross sectional area or the diameter of the column, which we denote by dt. So this packing factor is also important here, what type of packing we choose, so that this quantity is also it varies here. Then we calculate L prime. If we know L, we can take the ratios to obtain the diameter. If we know G prime, if we know G, actual G, we can take the ratios to obtain the cross sectional area. Alright, so this is a plot. Again, I repeat, it's very important, and you do at least one example to address this loading and flooding or the pressure drop per unit length basis. How much is the pressure drop? Because the pressure drop will decide what is the pumping requirement, say for liquid. Liquid trickles from the top. One of course makes use of this gravity, but generally you have to transfer this liquid from the ground, from the storage tank to the top of the column. Similarly, the gas flow rate, you require a blower. Okay, so there also energy is required. We need to know what is the size, not the kg per second, right? It's more important kg per second per meter square. That decides your superficial velocity, and in fact superficial velocity will decide your Reynolds number, mass transfer coefficient, etc. So it's a bit complex design. This is not a design course. Here we look at the two slightly different. I'm sure you have a design course or design lectures for very comprehensive design of distillation column or absorption columns, where you look at these quantities more rigorously. Okay, so let's get back to this mass transfer here. So if we look at now mass transfer, let's draw very quickly again. We have, now we work just on GS. We have already realized this is one. It's advantageous to work on GS, solid free basis. This is LS, and we have capital X1 here. Liquid comes from here at LS, and we have X2. So this is level 2, and the effluent gas after treatment remains at GS, and we have this Y2. At any cross section, we have X and we have Y, GS, 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 LS, LS, LS will remain the same. It's a solvent free basis. We can also make a note, Y1 is greater than Y greater than Y2. So this concentration was high, which has been brought back to this y, has been brought down to this y2. So it's essentially an absorption column. Just reverse of this would be desorption column or stripping. So there we have a gas which is, or liquid, which is very high concentration. So here if you go by absorptions, we have this concentration is x1 greater than x greater than x2. So pure solvent, nearly pure solvent becomes rich in the transferring component. Okay, desorption, the condition is reverse. Already we have a liquid which is a very high concentration of xt, x, and we want to strip in the opposite direction to the GS, etc. So qualitatively the treatment for absorption and desorption, they are the same here. So this is what we have as schematics. We are again interested in making, say, if you make it overall species balance, you will have very simple, similar to previous, recall GS y1 minus y2, we have LS x2 minus x1, and then all it means we can have operating line which will relate bulk phase concentration of one phase to another. So we can write GS y1 minus y. So all it means we have taken this envelope. Okay, so this is again LS x1 minus x. So one gets an operating line in terms of y equals mx plus c. This becomes your operating line. One can of course, just for your remembrance, alternatively we can also work on a small mole fractions, actual solid mole fractions. In that case the curve will not be linear. So we can write like y over 1 minus y. All we have done, we have substituted for y1 in terms of y1. We have ls x1 1 minus x1 minus x minus 1 over x here, but we make a note, it's not a straight line, not a straight line here. Okay, now there is another interesting thing here. When we make this mass balance, we also address one parameter or one design variable. It's called minimum liquid gas ratio. Okay, so we will address this first before getting into details of this mass transfer. Let's try to understand this with this graph. So we have x, we have y. Thermodynamics has given us y as a function of x, solubility curve, given x, how much is y if there is an equilibrium. We have this column, at the bottom we had 1, 2, we mark this as a gas, or liquid entering and the gas leaving from the top. So in general what you will have situations, very similar to the example which we took in the earlier class where we had the stage wise. Generally this would be given to us. Of course the problem can be formulated in different ways, but what is generally given to us, or most simplest would be that we know the gas flow rate. Okay, it's a practical problem. Gas flow rate composition is given. We have been asked to reduce the composition of this gas from one level to another level before we vent it. To do that, we have been given a pure solvent or solvent in which there is some very small amount of the transferring species concentrations. We have been asked to determine the diameter, height of the column, how much is the requirement of the solvent, and maybe what is the concentration of the liquid spent liquid which comes out of this. Let's mark those points. Okay, so all we are trying to say here that this y1 and this is your x1 here. Okay, and this is y2 and x2. So you must notice that the most common example would be, or scenarios would be, that y2 and x2 are known. We have been, y1 is given to us, we want to reduce this concentration from y1 to y2. To do that we have been given a solvent which is a very small concentration, approximately 0 here. So y2, x2 are known to us. Let's mark this point. So let us mark these points x2 and y2. You should also notice that x2 is smaller here, all right, and y2 is very small here, because y1 is larger than y2 and x1 is also larger than x2. Fresh solvent or nearly fresh solvent, very small concentrations, and the effluent has been treated and this level has been brought. So this point is fixed here. Now y1 is also given to us, so we mark y1 here. All we know in general, we know the GS. Okay, we have been given this liquid, but we do not know what is this amount of this liquid. That will be the most common scenarios. Okay, so now if y1 is given to us, we know this, we can mark the level here. Okay, but if x1, now all we know that, to go back to the operating curve, we have the slope of the curve given as ls by gs. Okay, and this curve, of course, we know it's a linear here. So if ls by gs is known to us and we want to draw this line, then typically we will have a curve like this. So this would be ls by gs. If we know ls, we can draw this line here, which is the operating curve, which will hit this concentration, this level at y1 to give us x1. So you understand what we are trying to say here, that if we know ls, liquid flow rate, or if we know the slope of this line, gs is given to us. If we know the slope, we can find ls. If we can find ls, we can draw this line here. Once we draw this line here, we have y1, we can find out x1, which is how much is the concentration of x1. So we know x1, y1, we will know x2, y2, and at any locations given x, we can find out what is y. Alternatively, if we know x1, what is the concentration here, we can mark this point, we can draw this line, and we can calculate ls by gs, which is the slope of the curve, and then we can, given x, we can find out y. We can address, how much is the driving force, maybe for y1. If we have to draw another line of kl by klg, that will give us interfacial concentration, etc. One can find the driving force. All right. So the second thing which we want to address here, now if we change the slope of this line, let's increase ls by gs. So if we increase the ls by gs, the line will move in this direction. What does it mean? If for a given gs, if we increase the slope, all it means the amount of liquid has increased, the liquid flow rate has increased, and if the liquid flow rate increase, you can see here that the concentrations x goes in this directions. Okay, let's note down this. For a given gs, so gs, kg per second, is known to us. If we increase this slope, ls by gs, if we increase this ratios of liquid to gs flow rate, then the x decreases, which is consistent with our understanding. If you take a very large liquid flow rate, then this concentration will be smaller. The liquid concentration at the exit liquid will be dilute here. So m increases, x decreases. And also we note that driving force, look at the driving force for mass transfer, that also increases. Look at the difference between the operating curve and the equilibrium curve as the line moves in this directions. Essentially driving force del y, if we call it y minus y star bulk phase, call from our previous discussion, that will increase here. And if this increases, driving force increases, the height of the column we will expect to decrease. Okay, so taking the large amount of the liquid, we have reduction in the height of this, and the concentration of the liquid exiting this column is also small. We will see what is the significance here in a minute. Let's take the second case. If we increase, now let's decrease the slope. That means given for a fixed gs, now our curve goes like this. Now if it moves in this direction, we just have the reverse effect. If m decreases or ls by gs decreases, amount of solvent is decreasing. If the amount of solvent decreases, mole fractions or the concentration of the spent liquor, that will increase. That's also expected because now we have a small amount of liquid, so the liquid will be more concentrated here. x will increase, but what happens to the driving force? Now the driving force decreases and the height of the column will increase. So we have two contradictions here. If we take a larger amount of the liquid, height of the column is smaller. If we take a small amount of the liquid, then the height of the column is very large, and at the same time the concentration here is also very large. We will see the significance of the spent liquor concentration, how does it affect our design. But right now let's just sum up very briefly that we are trying for a given gas flow rates, we are trying to determine what is the liquid flow rate, how does it change the height of this column. So if the liquid flow rate is increasing, pump cost will also increase. Okay, amount of the liquid or the cost of the solvent itself will also increase. So we have to pay more there if the amount of liquid or the liquid flow rate is large, but the height of the column will decrease. So that way we save the cost there. On the other hand, we take a very small amount of the liquid, we save on the solvent flow rate, pumping requirement, but height of the column will increase. So there is always an optimum, a scope of optimization. This is what we will do when you do a very rigorously designed course on the same design of an absorption column or a design of a distillation column. That's the economy. You're going to address it separately. Here in the mass transfer, we have seen the effect of the slope of the curve. How does the slope of the curve LS by GS affects the height of the column or affects the parameters like the liquid solvent flow rate or the spent liquor concentrations. Now very often it happens that when you have the spent liquors, you are not going to dispose just like this, because there will be environmental regulations. Okay, that spent liquor one has to recover, and one should make use of certain useful products. For example, if you get some certain concentrated sulfuric acids, or calcium sulfate, one can make certain crystals out of it. All right, so it's desirable that we have the effluent concentration, liquid effluent concentration, which is large. That's also for a mass transfer process. One we like to strip it. So for stripping or for desorption, that concentration should also be large, so that we have a larger driving force and we have a smaller desorption column, just opposite of this. So the economy plays a major role here. It's not one requires in fact some kind of programming to address these issues one by one. There's one more thing here which must address before we end this lecture here. We redraw equilibrium curve. So let's say that we have y versus x, and the shape of the curve is S shape. So let's say it's like this. Now let us mark the coordinates here. So we have y1. So this is the concentration of or the mole fraction of influent gas. So we are looking at 1 and 2 levels here. Gas gets in. So let's make it this is 2 here, this is 1. So let's make it 1 here and 2 here. So we have y1 concentration of incoming gas, y2 is the concentration or mole fraction of the treated gas. We have the liquid getting in here, solvent. So the mole fraction or the concentration is x2, and the spent solvent leaves from here with the concentration or mole fraction x1 here. All right. So we have y1 here, and this is the y2. Let's mark it here y2, and corresponding to this coordinate we have this x2. So the mole fraction or the concentration of the solvent. All right. So this x2 is concentration of solvent here. Now what we have to do is to find out if you have a general operating curve, then we will have the operating line something like this with the slope here as LS by GS. Now in this case, when the shape of the curve is like S shape here, then we have to be careful in the sense that from here we have to draw a tangent like this to this curve here. In other words, we can see that there is a pinch here where the driving force for mass transfer del y or a small del y, this has become 0 here. So the driving force is 0 here, and we require infinitely long column here. So the idea here is that the corresponding to this pinch, what concentration we will get here as x1, that will be x1 min, So this is the maximum concentration of your spent solvent. So this is the maximum concentration or the mole fraction of the spent solvent here, or the spent liquid. All right. So if we take the slope here, this will correspond to Ls by Gs minimum. In other words, if we decrease the liquid amount or liquid flow rates, then the curve will move in this direction, the operating line will move in this direction till it makes a tangent here. If we try to connect this point y2 x2 with all the way till here, where this curve has intersected this y1 line, this will give erroneous or wrong result here. So this has to be discarded. All right. Instead of this, one has to find a tangent which will give you x min. Once we know this Ls Gs by min, then we can write Ls by Gs operating equal to maybe 1.5 or 1.2 times. This would be prescribed Ls by Gs minimum. All right. So once we get this minimum solvent, so then you find 1.5 times, find a new operating curves which would be anywhere like this here. All right. So our strategy is straightforward. Steps are straightforward. One, first determine Ls by Gs min from tangent, what we call pinch. All right. So we must be careful. First we should inspect and see the shape of the curve, which is like S shaped. All right. So in this case, somewhere here there will be a tangent. Okay. If you try to connect right from here with this point like this, that will give you a wrong result here. So first get this Ls by Gs min, find the tangent point. Number two, find Ls by Gs operating equal to 1.5, for example, Ls by Gs min. Then from this, once we get the operating curve, say it's like this, from here we can get x1, which is the concentration or the mole fraction of spent solvent. So alternatively, we can write down the operating line equation. Ls x2 minus x1, we have done this earlier, Gs y1 minus y2. So Gs is given, y1, y2 are given. Ls we have found out from Ls by Gs operating, which we found out from 1.5 times minimum Ls by Gs minimum. So we know Ls, we know x2, we can determine x1. So idea is that x1 concentration of this spent solvent can be determined graphically from reading here, all right, or we can determine from the equations. All right. Once we have this operating line y versus x, we have this equilibrium curve here, and we have this operating line, then we can answer NTU. We can determine what is NTU. We can determine height of a transfer unit, all right, or the height of this column. So we end today's lecture right here. Thank you.